Just a couple of announcements before we start the show. If you haven't picked up a ticket for the Open Data Science Conference in Boston, there's still time. It's happening from May 3rd through the 5th, and it's a great chance to learn more about data science and data engineering. You can also now get a t-shirt and help support the show by going to teespring.com/podcastinit. You can also pick up a mug and a sweatshirt while you're at it. Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at linode.com/podcastinit and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app or trying out something you hear about on the show. You can visit our site at www.podcastinit.com to subscribe to the show, sign up for the newsletter, read the show notes, and get in touch. To help other people find the show, you can leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host, as usual, is Tobias Macey, and today I'm interviewing Nathan Goldbaum and John Zuhone about the YT project for multidimensional data analysis. John, could you start us off by introducing yourself?
Hi, I'm John Zuhone. I'm an astrophysicist and a computational scientist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts.
Nathan, how about yourself?
Hi, my name is Nathan Goldbaum. I'm a postdoc at the National Center for Supercomputing Applications at the University of Illinois in Urbana-Champaign.
And could you guys tell me how you first got introduced to Python? John, how about you go first again?
I got introduced to Python while I was a graduate student. I was running a simulation code and I needed to parse a log file. And I came to a postdoc and I said, I don't know what the best tool is to parse the log file. And he the tool of his choice was Python. And so he started writing a Python script and just sort of explained it to me along the way. And kind of got hooked on it, I think, because I found it a really powerful but also really easy language to learn.
And Nathan, do you remember how you got started?
Yeah, so before I used Python, I was mostly using IDL, which is this awful language that basically only astronomers use, maybe a few other domain scientists, but basically astronomers. And it's closed source, so you have to pay a license, or your academic department pays a license fee for you, and just kind of awful to use and is a terrible language. So in the middle of grad school, I realized that I was using this awful proprietary language, and I should probably learn something that's more marketable and also just less awful. So at the same time, I was starting to work with big simulation data sets, and I realized that there was this library, YT, that I could use if I was using Python. So I sort of picked up Python and YT at the same time, like in 2012.
And that leads us nicely into the question of what is YT and how did it get started?
Oh, yeah, sure. So YT is a package that was developed initially by Matt Turk, who's also at the University of Illinois. And it's a Python package for analyzing multidimensional volumetric data. So I guess I should sort of explain maybe those two terms and unpack them a little bit. So by multidimensional, at the moment, we mainly mean three-dimensional data. So you have you imagine basically a simulation box where you've got, two stars colliding or, structure in the universe forming, or you can imagine like a 2D plane where you've got like a shock tube where a wind is blowing and, hitting a impediment and basically forming a lot of interesting structure. And by volumetric data, I guess that's also what I mean, is that we're thinking about things that are spread out in some kind of space. Normally we think about that in terms of like the three spatial dimensions, but we're also moving into domains where we think about, thinking about different dimensions in terms of, other things besides length, width, and height. Let's say that one of the dimensions along the box is time.
I can't hear John anymore.
Sorry, Nathan?
You started to get a little bit choppy through there. I heard you up through saying we're starting to get into areas where, and then you started to cut out.
Okay. We're starting to get into areas where we don't just think of the dimensions in terms of length, width, and height, but we also think of dimensions that are not spatial dimensions. We're thinking about, let's say you have a data set that has a time dimension, and sort of treating that as a dimension that you would, take a slice on, or make examine a subset of, or maybe even, we have in astronomy, we have data cubes where the two dimensions are the two directions on the sky, and then the third direction is, say, velocity along the line of sight. That's also a very common data set. So basically, we're thinking about how to look at complex multidimensional data sets in an intuitive way that is a way that scientists and physicists would prefer to think about it, as opposed to thinking about it just from like a coding perspective.
YT's bread and butter is working with really complex research data sets. So these are data that are output by research codes. So the person that designed the data set might not have been trained in how to do that well, or it might be extremely complex for other reasons or whatever. So you have this very complex data set on disk, which might be really difficult to work with. YT can parse it and understand it and present it to you in a manner that allows you to ask questions about it in a physically motivated way. Like, what is the total mass of gas contained in this sphere? That's like a really basic YT operation. Or I want to visualize a slice through this simulation, or a projection, or do some sort of more sophisticated, complicated volume rendering, that sort of thing. So it's the ability to take parsers for real-world research data formats and then ask questions about that research data format without having to write your own analysis software that needs to parse this complicated research data format, and then on top of that, do some sort of analysis routine that, some sort of an algorithm that you could implement yourself, or you could use some sort of community software to do. So like basically every grad student who ever works with these complicated research data formats basically is re-implementing the same parsers and re-implementing the same analysis algorithm code, when instead it would be much better if everybody was pooling their resources into a community code, which is sort of like what YT tries to be.
And was there any sort of pre-existing tooling or set of best practices that YT is replacing from other languages, or that's more specific to the scientific domain?
I'll make a comment about that. So in astronomy, there's a lot of roll your own type attitude where we've got this, as Nathan was talking about, we have these complex data sets, and they're often in very common file formats. Like one file format is HDF5 that's used a lot. And so there are some industry standards in terms of that, but when it gets to when people decide how they want to read that data, it's very much, they write something on their own and they just kind of, special purpose it for whatever purpose they were thinking of when they're like, okay, I need to read, say, the velocities out of this data set, and I need to figure out the average velocity in, say, a rectangular region or something. And I think what the philosophy behind YT is that it turns out that you might write a code like that, and then you determine that you need the code to do something slightly different. And so instead of a rectangular solid, maybe I need a sphere, or maybe instead of the velocities, I need to read the density or the temperature or something. So the idea behind YT is to take these very common operations, generalize them, express them in a language that allows you to ask questions of the data in sort of a physics sort of way. So, for example, asking questions about spheres and rectangular solids and slices and that sort of thing, and prevents you from having to sort of reinvent the wheel all the time.
Can you explain a bit about the name and where that came from? Because having a two-letter name for a project is a little bit enigmatic.
I think that's true, yeah. So the original author of the code base is Matt Turk, who's my advisor at the University of Illinois for my postdoc. He wrote it for his PhD like in 2008 or so. So like it's sort of a whimsical name because he didn't expect it to be used by lots of people. It just turned out to be useful, and we sort of kept the name. So it stands for yours truly, but it's also a reference to the Neil Stephenson novel Snow Crash. And that makes more sense if you realize that it was originally written to analyze outputs from a simulation code named Enzo, which Matt was also using for his PhD. So YT is Enzo's helper in that novel. But yeah, it's also a substring of Python, which is nice.
It's a surprisingly deep level of complexity combined with those two little letters. So it sounds like one of the primary use cases for YT is for analyzing astronomical data. So I'm wondering how it compares or interfaces with other projects in the Python ecosystem, such as AstroPy for doing data analysis of astronomy.
Sure. So AstroPy is mostly there for working with data that comes from a telescope. So that means like doing math on the surface of a sphere, or timekeeping, really, really accurate timekeeping, or like figuring out different coordinate systems on the sphere, like trying to find what object is contained inside a circle. That's what AstroPy is there for, as well as many, many other things. YT is there for analyzing the outputs of research simulations. So sort of the sorts of simulations you might run for your PhD or as part of a huge research project where the simulations are run, like a really common thing that big efforts at national labs in order to push forward cosmology programs is to run really, really enormous cosmological simulations and then use those cosmology simulations as input for parameter estimation in the physics problem. So you have this enormous cosmology simulation you need to work with, or there's lots of other reasons you might want to run a cosmology simulation. That's just one. So you end up with gigabytes and gigabytes of this complicated data that you need to process in some way. And YT is there as the toolkit that you need in order to answer physical questions about that data.
I think an important point in this context is that often you have this gigabytes and gigabytes of data, and at any given time, you don't need all of the data that's in that data set to answer the particular question you have. And so the good thing about YT is it's designed to work only with the data that you are interested in. So say a spatial subset of the data or only certain physical quantities that are in the data. And this is good because it sort of, boxes in the simplifies the questions that you need to ask, but also rather importantly for these kinds of data sets is that it avoids having to read in all of the memory of this giant data set in at once when in reality you maybe just need like a small subset of. And so it's designed to sort of make your job simpler and also make the computer's job a lot easier too, not using quite as much memory and not spending as much time that you would need to do if you were reading in all that stuff just to use a small subset of.
And the trick for that is that the I/O masking is spatial. So if you only want a certain subset of a data set, we know where on disk in that data set that data comes from. We only need to do I/O for a small subset. And doing that in increasingly clever ways is basically how YT can get faster.
And so at a high level, is it fair to say that AstroPy is more for observational analysis of data, whereas YT is more for theoretical research?
That's a good way of characterizing it, I think.
And aside from astronomy, are there any other domains where YT is widely used?
Although there are, so this sort of is a good segue, I guess. There are astronomical data sets where YT is great. So John brought this up earlier. Position velocity data is something you get a lot in astronomy. So like from a radio telescope. So what a radio telescope actually sees is at different places on the sky, there's different the emission at different frequencies, and those frequencies correspond to different velocities along the line of sight. So you can map the data that comes out of a radio telescope into a position velocity, a 3D data cube, which you can use YT to look at, like do slices or projections or different sub-selections of the data. There are other tools that do similar things like that. That sort of regular gridded data isn't where YT really shines. YT really shines with adaptive multi-resolution data. So like data that has some sort of, it's coarse in places and then in other places it's very refined and high resolution. It's tricky to do spatial aware chunking on a data set like that because it's structured, but it's structured in a very complicated way.
And are there domains outside of astronomy where YT is popular or widely used?
I don't know if I'd say widely used. I know that there are other areas in which it's being used for certain applications. I know that Matt, who we referred to earlier, has actually used it to volume render Earth data from an earthquake simulation that I thought was fairly interesting.
That went into a project called Seismodome, which is something you can Google.
I've also seen. I don't think there was any serious analysis done on it, but brain scans have a length, width, and depth to them, and there's a YT volume rendering of a brain scan as well that I thought was pretty interesting.
It's also used by a lot of nuclear physicists, so people that are simulating nuclear reactors. So there was a big effort a year or two ago to add support for unstructured mesh data. So YT now has support to do second order interpolation on various kinds of unstructured meshes and is being used right now to simulate molten salt reactors by one student in our research group. And then I know it was used to simulate ITER and some, like, I don't remember the details, but by people at the University of Wisconsin. So there's sort of a growing community of people that are doing it in nuclear physics. And then we'd also like to sort of expand to other fields. There are plenty of other people, especially like people that are doing CFD simulations that have data that YT could work with. It's just a matter of writing readers and also there's a lot of things in YT that are very astronomically focused. Going forward, we're thinking about ways to make YT less, or like keep the astronomical focus stuff, but make it possible to have a focus in other domain sciences. So sort of if you load, like you loaded a weather simulation, then you would be able to like have weather specific analysis tools or fields. We haven't talked about fields yet, but fields are really important in YT. So like predefined things that people commonly work with in your domain that you can access in your data set.
And one of the main use cases, or at least one of the use cases that was highlighted in the documentation, is the ability to visualize multidimensional data. So I'm wondering, what are some of the overall design challenges that are presented when trying to represent such complicated domains using a visual model?
I would say that the first one is that you kind of have to have a good sense, at least the end user, they need to have a good sense of like what kind of visualization they want to do, right? So they might only care about like a two-dimensional slice, for example, or in astronomy, we have three-dimensional simulations, but of course we don't deal with things in three dimensions on the sky. Things are projected onto the sky, and so we have a projection operation where you basically just integrate along one dimension and down to a two-dimensional map, and then we have also volume renderings. And so there's where you're just, you have a 3D volume rendering of, different surfaces of a particular field within the domain. And the thing is that these are a common set of operations that various people with various types of data sets would be interested in. And the challenge is that because the data sets can be so very different, a uniform mesh or a adaptive mesh or an unstructured mesh or a set of particles, for example, we have to sort of figure out a way to make the underlying structure of the code take these common operations that we present in the same way to every user and still do the same stuff under the hood on the very different types of data. And I think that's a big challenge. I think it's a challenge that we're still grappling with in certain types of data sets.
So here's a really concrete example is I want to create a plot of a slice through my simulation. And there are a number of ways that you could construct that visualizations. So like probably the simplest one would just be creating the pixelized representation of that slice. So you have like a 2D uniform resolution array, and just generating that slice, when that slice can come from particle data, unstructured mesh data, adaptive mesh refinement data, and then uniform resolution data, architecting the code so that it can generate from the same interface that result is that's sort of the complexity that John was just alluding to. And then on top of that, once you have that image can represent lots of physically meaningful things. Like you could just export the image and just let people construct their own plots. But what people commonly want to do is have like color bar and like axes and a title and like annotations because something is interesting inside of the image. So we have this whole wrapper around Matplotlib. It's called the plot window interface that lets you create these sorts of, and the idea is that you're sort of making a window into the data. And it's got annotated axes, so you have the spatial scale and a color bar with a label that corresponds to whatever field you are asking for. And that label has units. All the axes have units. Just making so that works and makes sense and works with many different kinds of data and many different sorts of visualizations of data in a consistent way can get really complex, but also it's sort of magical when you write a 3-line script and then you're able to make this nice slice plot that maybe is publication quality, kind of. I don't know if it's quite there, but it's I think it's pretty high quality.
Digging into a bit of the guts of YT, what does the overall architecture or design look like, and what are some of the biggest challenges that you have faced in the process of developing the project?
So there's the repo is sort of split into the sort of core data structures, the thing that represents the data set itself. So that's a thing in our documentation we refer to as DS usually. DS equals yt.load some path to some data set. So that this is like a Python object that conceptually represents the data set, and you do things with that data set object in order to access the data that it represents or do things with it. So there's sort of that, and then all the things that hang off of it. And then there's the front ends. So those are the parsers for these research data formats. Because YT has this concept of like trying to map semantic meaning onto the data. So we need to understand the data at a pretty high level. So like we need to know like this field means the gas density field and has units of gram per centimeter cubed, and we need to read it as from this place on disk. And that's different for each data format. So there's a bunch of different front ends. And then next to that, there's the analysis modules, which is sort of an attic of things that people have developed. And we're actually trying to split those off into other repositories so that they can, those are things that people developed a long time ago and then sort of threw over the wall and we're trying to maintain it, but it's also, difficult to maintain stuff like that. So going forward, it's going to be mostly just the core and the readers. And then also, on top of that as well, is the field system. So fields in YT are, you want to construct some, like, for example, the kinetic energy. That depends on things that you might read off of disk, like the mass and the velocity. So you need to construct that by doing some sort of operation. And we have lots of predefined fields and systems for defining these fields in a sort of automatic way. Because that, like the field definitions might depend on different properties of the data set, so they need to specialize themselves depending on what sort of data we're reading. I think that's it. Did I miss anything, John?
I think one of the things I'd like to highlight a little bit of, since I've worked on it a lot and also find it probably one of the more fascinating parts of the code, is the unit system. So, physicists work with things in many different kinds of units, right? So you have time units like seconds and hours, or mass units like grams, or in the case of astrophysics, solar masses. And, the interesting thing about these calculations is, before YT, basically I have all of these, arrays in my analysis code that I was multiplying together, and say I needed to get from density and temperature, or say magnetic field, to some kind of like intensity of light or something from an astronomical object. And so I'd multiply all these numbers together, and I would have to check very meticulously, and often fail at getting the units right, because I would be multiplying these numbers with a lot of different mathematical operations, and including physical constants, and doing everything by hand, and usually getting the units wrong on several different things. And the YT uses the Python package SymPy in a symbolic units implementation, basically, where you have NumPy arrays, or just like single floating point numbers that are associated with units. So for example, you might have a number that has a velocity of kilometers per second, or you might have an array that has a temperature in Kelvin, and you can multiply and add and combine in a number of different mathematical operations with physical constants. And the number you get at the end is in units that are actually the correct units given the mathematical operations. So you take the square root of the gravitational potential energy, by the way, it turns out that that has the units of a velocity squared. So you can convert that into, kilometers per second. And all of this happens, now all of this happens fairly seamlessly, but it turns out to make a system that works and takes care of all the intricacies of physical units, which turn out to be a lot more than I think the average person anticipates. It takes a lot of work by a lot of different people. For example, there are different electromagnetic systems of units for measuring things like current and charge and magnetic field, and they're not necessarily compatible with each other. So one of the things we had to do is figure out how to have these different unit systems live side by side with each other, but also make appropriate translations between them, even if the certain things are not necessarily even dimensionally equivalent.
And getting that last bit right is extremely important for people that do things like magnetohydrodynamic simulations, which it turns out is kind of popular. That there are lots of people that do simulations like that. So you need to get those details right, or they notice.
Yeah, that's right. We did have we have a couple of ways that people can get to us for user support. And I remember the day that this came up on our I think it was on our IRC channel, where the units for the magnetic field were not being converted properly, and so that was something we had to look into. But I just think it's fascinating how it took, as I said, it took a lot of work by a lot of different people, but now it's like one of the most impressive features that I always like to show off in YT to physicists, because they're like, wow, you just multiplied those numbers and it gave, say, the pressure in the units I expected it to. So
I should say there are several other projects that do similar stuff, like Pint and AstroPy. This is a case of convergent evolution. I think Pint existed when we started working on this, but there was some, it wasn't getting lots of commits. I don't remember the details, but we ended up going with this other library that this grad student who was participating in YT a lot a couple years ago, named Casey Stark, wrote, that wrapped SymPy, and we sort of absorbed it into YT and improved it. So it's, unfortunately, there are lots of different implementations of these units libraries, but we think ours is pretty great.
Yeah, I'm forgetting which episode it was exactly, but I was speaking with someone else recently where they were leveraging Pint, and I was asking about its relation or comparison to the unit's capabilities in AstroPy. And one of the things that they commented on is that while at face value units are units, once you start getting more involved with them, there are so many different edge cases that are necessary to consider that one units package isn't necessarily going to do full justice to the particular domain in which it's being applied.
That's definitely true. And having the ability to rip out the guts of the units implementation that we were using and like adjust it to our use case was really nice. So basically vendoring this library into YT and then making it sort of absorbing it into the rest of the code base and making it sort of integrated as much as possible is really useful. And maybe having an upstream dealing with an upstream project that's, might make decisions that you wouldn't make isn't the best for that sort of thing.
Oh, I was just going to point out that an interesting case of that is simulations of Einstein's theory of general relativity. Numerical relativists have a habit of saying that, okay, the Newtonian gravitational constant and the speed of light are equal to 1. And they like measuring things like lengths and times in terms of the mass of the sun, for example. And because everything is just simpler if you take all these pesky constants, you just set them equal to 1 and then maybe make adjustments at the end. And so that's something that we have a little bit of support for. I wouldn't argue that it's maybe ideal, but it was definitely an interesting challenge. Is how do you how do you think about things like within the framework we have, how do you think about things that are fundamentally different dimensions, but give them units as if they are, basically. So
numerical relativists have really complex data, both maybe not surprisingly, but both conceptually and also just like the representation on disk is really complicated because they're simulating things like black holes, so trying to simulate infinities is hard.
And you guys have touched on it a little bit, but some of the sample data sets that I was looking at in your examples are fairly substantial in size. So I'm wondering, what are some of the biggest challenges associated with trying to run analyses on such large amounts of information?
So the first problem is getting it done before the end of the universe. So, and that can be accomplished either by making each bit of the analysis faster and also by doing the analysis in parallel. So YT tries to be both very fast and also parallel aware. Using the library MPI4Pi, which is built on the message passing interface, which is really so you would, if you were on a system where you had a really enormous data set, you would have access to an MPI library because it's really commonly used to produce simulation data sets like that. And that sort of is another challenge. Just moving data around can start to be extremely difficult. Once it gets to like the terabyte size, you don't want to move that much data across the country. It takes a very long time. So you want to keep the data wherever it was produced and then analyze it in situ, preferably in parallel.
Yeah, I think that's something that's important to point out is that most of maybe not all, but many of these data sets you're referring to were produced using, thousands of cores on a supercomputer. And so, often if you want to do like global analysis, in YT, it will take, as Nathan's referring to, it will take doing operations in parallel, which YT supports. But again, the nice thing about YT is that, if I have this giant data set and I only am curious about, say, like a few parts of the simulation domain, say there's like maybe this big domain, but maybe a few galaxy clusters formed that I only want to look at those, then YT knows how to figure out where the data is from those particular parts of the simulation domain and only download the cells and or particles it needs from those locations. And you can just kind of leave the rest of the giant data set behind.
And also, it's not only, so John and I are working together on a research project, and during the process of this research project, we've managed to produce 500 gigabyte data sets, I think, something along those sizes. So it's not every day that you're working with data that huge, and data that huge has its own challenges. But it's often the case that you're working with a time series that can be really large, or so like. For my thesis, I publicly released this 14 terabyte data set that was each individual datum in that data set is a 5 gigabyte file, which is one snapshot in the evolution of a galaxy like the Milky Way. And you can get lots of interesting scientific discovery if you have lots and lots of time steps. So that's both by watching the thing as it evolves and also getting really fine time resolution for different sort of analyses. Yeah, so being able to analyze a big time series like that in parallel is really important. And YT has parallelism primitives that allow you to easily iterate over a simulation time series. And that can also be more complicated as well for things like a cosmology simulation where your time output is linked to the redshift, which doesn't have anything to do with like the time. So being able to analyze that at certain precise redshift values, you need to be able to have some sort of smart indexing system, which YT also will help you out with.
And how has the project evolved overall from when it was first created and in the time that you guys have been working on it? And what are some of the biggest challenges that you see that it's going to face in the future?
So I'd say the biggest challenge will be, trying to expand beyond our niche. So right now we're mostly dealing with astronomical data, so astronomical simulation data, which is it's a community that maybe has a couple hundred, maybe even as much as 1,000 researchers in it. But I think YT's potential for enhancing discovery in these sorts of simulation data sets can be expanded way beyond astronomy. So I think a big challenge for us is figuring out how we as a community can incorporate many different perspectives and then break all the assumptions that we're currently making in order to make it so that YT can make sense to work with data from many different kinds of fields.
I was just going to say that one of those assumptions that we're working with right now is that most of the data sets that we're really good at analyzing are in 3 dimensions and in Cartesian coordinates, so X, Y, and Z, basically. And there are a lot of research groups, both in astrophysics and otherwise, that have coordinate systems for their data sets that are, in, say, spherical coordinates or cylindrical coordinates or, even, more unusual coordinate transformations. And so when you are thinking about the operations we were talking about earlier, like making slices and projections and volume renderings, it's sort of easy to sort of I guess I'm under the assumption that I sort of see the world as Cartesian, basically, to first approximation. That's the way I think about the world. So it's easy for me to think about having to do all those operations under that kind of coordinate assumption. But trying to translate those concepts over to these other kinds of data sets, I think, is a really challenging thing, but a necessary thing to do, because there are many calculations that are just simply much more convenient in those coordinate systems. And as I was sort of referring to earlier, some data sets they're not even properly spatial, or there might even be a case where we decide we want to look at, a 4-dimensional data set. So imagine, we can treat a set of 3-dimensional data sets as a 4-dimensional data set where you have length, width, height, and time.
And how has the project evolved? So it started out as a sort of a personal toolkit that one person was doing for their own thesis, and then sort of quickly several other people in his research group also chipped in and helped out in various ways. Then more and more other people that were using ENSO, the simulation code I mentioned earlier that YT was originally written to work with. ENSO is a publicly available adaptive mesh refinement hydrodynamics code. So it sort of has the same principles about openness that YT does. So it's sort of the people that are working with ENSO were also sort of interested in working with YT as well. Yeah, so that sort of extended to that community, and then we gained support for many different data formats beyond ENSO, and that sort of expanded that community. So the project has evolved sort of by supporting more and more different kinds of data, and also bringing in as contributors the people that are actually working with that data. So it's the people that know how whatever research algorithms they want YT to perform, how it should be performed, and then also the people that know have crazy data that YT fails with, so we can fix bugs or realize that there's things that we need to do to change the way we do things because we're making an assumption that's broken by some data that actually exists in the real world.
All right, do either of you have anything else on that particular subject that you'd like to expound upon a bit more?
I guess I just want to emphasize that YT is a community. It's mostly domain scientists that are contributing to YT. There are a few people, basically me, that are actually paid to work on YT, but almost everybody else, and also over the history of the code, the people that were contributing mostly to YT are using it because their contributions solve real world research problems. So I want to emphasize that YT is a community project. And it's there. We're standing on the shoulders of giants and all the people that have contributed over the years. I think we're up to more than 100 people now.
Yeah, and in fact, I just want to emphasize, that as well, in the sense that working with this community and people like Nathan and Matt, who we mentioned earlier, and many others, I've become a much better programmer, software engineer, much better scientist by interacting with all of these folks and learning just better coding practices, and how to work as a team. Has helped me immensely. in terms of like the job that I'm working at now, I think I've learned a lot from just working with the team at YT that has helped me in that area as well. And so I think it's a really important and integral part of like what makes the software package work is the openness of the community and the fact that people who are, not just interested in working on code, although as fun as that is, people who are actually using it for the sorts of problems that, other people may be interested in, I think is what makes it work.
And are there any other topics that we think we should cover before we start to close out the show?
I'd just like to make a comment about something kind of neat that I think is happening in that. Every 10 years, NASA has a decadal survey and new flagship level missions are proposed. And I'm part of a group that's proposing a new X-ray telescope for the next decadal survey. And YT is actually a very integral part of developing the science case because we're taking 3D simulations and we're using YT to read these simulations because these simulations come from a very large number of different codes, and the common thing that is able to read them all is YT. And then we have other packages that we can use with YT to create simulated X-ray observations. And I was actually spending all of my day today working with X-ray astronomers who are trying to make really cool images and other data products of what we would actually get to see in the universe. In this case, it was galaxies, assuming that we had this wonderful instrument that we're proposing. And so I think that it's just sort of an example of how something that started off a tool with limited application has turned out to be a much bigger thing that's having a broader impact.
All right. Nathan, anything else?
No, that's really awesome, John. I didn't know that. That's really cool.
So for anybody who wants to follow either of you and follow what you're up to, I'll ask you guys to just either add your contact information to the show notes or send it to me so I can add it. And with that, I will move us to the picks. My pick for this week is a project I came across recently called Scout 2, which is a simple command line tool that will read in your credentials for AWS and then scan through your account to try and see if there are any configurations that will lead to any sort of security vulnerabilities, and then it gives you a nice HTML formatted report to click around and explore in. So it's an easy way to just do a very quick heuristic of is there any low-hanging fruit that I need to address in my AWS account? And as somebody who works in the operations space, it's definitely very useful to be able to get that kind of information quickly and easily. And with that, I'll pass it to you, Nathan. Do you have any picks for us this week?
Yeah, so I'm currently reading the Expanse novels, which are really awesome. If you like the TV show, you should read the novels because they're better.
John, do you have anything?
Maybe this might surprise some of your listeners, but I'm actually finding that one of the best code editors I've used in a long time is Visual Studio Code by Microsoft, which I'm guessing that some listeners might be falling over at this point. But it's an open source project. They've open sourced it on GitHub, and I'm finding it to actually be a really powerful editor. And they've developed a pretty sophisticated plugin system with support for many different languages. And I'm just finding it very enjoyable to use. And so when I talking with other people who are doing Python programming or in other languages, I say, hey, actually, this is a pretty cool editor that you should check out. And, if it's missing some feature you like, then you should, you can actually develop it and send them a pull request, which I think is a neat thing that they're doing. So.
All right. Well, I really appreciate the both of you taking time out of your day to come and join me today, despite the scheduling difficulties. And I hope you enjoy the rest of your evenings. I'm sure that the listeners will greatly enjoy hearing about the ways that YT is being used for astronomical research.
Thanks for having us on.
Thank you very much.